that, please. Okay, physics. DIFC physics. Fields and induction. How many questions were there?
5.
5? That's more like normal.
But the last one is 5 4.
Yeah. That seems like normal. Okay. Well, maybe you can give me the first question, Mr. Sharif, there. What is it?
A power plant produces an AC current of voltage at 110 volts. What is the maximum voltage of that current?
Yeah, so that you multiply this by root 2 and we get our answer. So can you give me that, please?
Yeah.
Where's your calculator? Come on.
110 by 300 no 155.5.
2.
1 meter cable.
It's good, it's good. I have it now, thanks. Okay. So here we have Faraday's law, but we won't worry about the n. There's only one loop, and we won't worry about the minus. So it's just this. And we know what this is, 3. No, it's 2. And what's changing here? The area. If you look at the manhole cover, what is it? 1 meter this way, and 3 centimeters this way. So this moves up. So it's the area that changes. So this would be B change in area over 2. So at the beginning there's no area, and then you move it up and you get some area here. How much area?
1 meter and
1, yeah. B times 1 times 0.03 over 2. So this will equal whatever 0.03 over 2 is times B, and B here is 0.07 times 10 to the minus 3. 1.05 10 to the minus 6. So that's micro volts. Okay. 3 now. A 2 meter horizontal copper pipe is dropped from 100 meters. So what is the EMF here? Okay, can I scroll down? Yeah. So you have your pipe. It's 2 meters, and it's dropped a distance of 100 meters. So clearly here the area is changing. At the very beginning there's no area. Then as the pipe falls through the air, it draws out an area. Let's get the time first. UVATS. U 0 V, don't know A, minus 9.81 T, don't know S, minus 100. S equals U T plus a half A T squared. So T is 200 over 9.81 root. So that's the time then. 4.52 seconds. Okay. So now, using Faraday again, the voltage will be change in flux over time, which is change in flux over 4.52, which will be B times change in area over 4.52, which will be 0.07 times 10 to the minus 3 over 4.52 change in area. So we go from no area to a lot of area, 200 in 4.52 seconds.
3.09 times 10 to the minus
3. 3.09? Okay. Got that? I can scroll down? Yeah? Yes? Okay, so now we're on to a copper wire. A copper wire is wrapped around a circular loop 100 times of radius 5 centimeters around a magnet. Okay, so let me picture this. So you have a magnet north-south, and then you have, maybe it's like this, it's inside a loop, a circular loop. Yeah, and then the magnet's removed. So then you take the magnet out, and it takes a quarter of a second to remove it, and the field density here is 2 Tesla, and the wire that wraps around the outside here wraps around 100 times. So Faraday says the voltage would be, I won't worry about the minus again, N delta phi over delta T, which in this case is 100 over 0.25 delta phi. Now, in this one, it's not the area that changes, but the magnetic field density, because at the beginning you have 2 Tesla, but then, sorry, that's a B, but then at the end there's 0 Tesla because you remove the magnet. So it's the magnetic field density that's changing here, not the area. So if I put that underneath here, that would be 400, and then the change, that would be A times the change in B, and the A is pi r squared.
What is the 400?
This 5 pi r squared is the area, and then the change is 2, or really minus 2, I suppose, because we lose 2, we go from 2 to 0, but we're not worried about the minus right now. So that would be 800 pi, and this is 1 over 20 squared over 400, I think, 2 pi, about 6.28 volts. I don't know, if you type this in, this is 6.28?
Yes.
Yeah.
2 pi.
2 pi, correct, yeah. I don't know if I was saying what is normal in the exam, but this is a very typical, this one is a typical section A question. You know, a magnet's in a pipe and you remove the magnet from the pipe. What's the induced current in the wire that's wrapped around 100 times? Something like that. This I've seen a couple of times in the exam. The ones where you have something dropped from the sky, I don't really see that so much, maybe once or twice. It's this one that they like to ask. Okay, do you have this? I can do the next one, yeah. So the next one is, last one, 5. Okay, I can go on to 5. So let's drop what we have here. A small generator uses a magnet of flux density 5 Tesla. Okay, so we have a north, we have a south, and we have a magnetic field of density 5 Tesla. The rotating plane is a small 30 by 10 rectangle. So I'll just draw it like this. But if I was to look from it from the ceiling, there's north, there's south, and you have a rectangle here, and this side is, we'll say 10. I suppose I should have made it clear which one's the 30 and which one's the 10. But it's usually longer this way. That one's 30. Okay. And there's 10 loops on it. So the wire that's on it wraps around 10 times and then comes out. So we know the n is 10. Oh, I wrote that there. N is 10. What else are we told? The plane moves from a vertical position to a horizontal position. So really at the very beginning it actually starts off like this. And then it rotates this way. So it's actually starting like this. And the rotation is rotates with 50 Hertz. So that means in 1 second it rotates 50 times. First question, what is the flux linkage when the plane is vertical? Which is like this one here. Okay, so we have our formula. What is it? NBA, isn't it? Flux linkage is NBA. And there's a cos theta in here, but I don't think we... Yeah. Yeah, it's at an angle, but this one is good because it's... Yeah, it's all what we need, yeah. I suppose we could put in cos theta and the angle is 0. The plane is pointing horizontally, so it's 0, but we won't bother. Okay, so that's 10, 5, 0.1, 0.3. So that's 0.15? No, 1.5 is it?
Mm. 1.5.
Yeah. Okay. What is the flux linkage when it's horizontal? Okay. So if it rotates 90 degrees, then it's NBA cos 90. I don't even need to check that because I know cos 90 is 0. So it's 0 Webers when it's in this position. See? So this is in this position. This one's in this position. What is the time taken to go from the horizontal to the vertical? Well, I told you the periodic time is 1 over f, which is 1 over 50, which is 0.02 seconds. However, that's hard to do one loop. How much of a loop is it to go from vertical to horizontal? Quarter. So the time... 5 milliseconds, is it? Yeah, it'd be 1 over 200. Yeah, 5 milliseconds. Great. Okay. Okay, is the last part calculate the voltage? Probably. I feel like that's what I'm building up to. Yeah? You're dying soon. Do you mind just doing it in my classroom though? Because we'll make a mess. If you could wait till you're outside, it'd be better. Thanks. No, of course not. How sad my days would be if I didn't have Mir. Who would cheer me up in the morning? Yes? With your story of how long it took to get from Rathmines. Alright, so the T here is this divided by 4, what did you say, 5 milliseconds? 5 milliseconds. Okay, and lastly D is going to be, what is the voltage? Okay, so the voltage is N times delta phi over delta T. Now, I don't really need to put the N in because, why not, do you think? No, not because of that. You see, what I'm going to be doing is, I'm going to be looking at this one changes to this one. It goes from 1.5 to 0. But why do I not put the N in? Why do I not put in 10 here for the N? Any ideas? The reason is, the N is already included in this. So I'll be putting it in twice. So this here, the reason the N is here is because this should be the total flux, but these are already totals because it includes the N. So we don't need to put the N in twice. Yeah. So what would that be? 1.5 over 5. Is that 3 kilo? 300. 300 volts, yeah. Now, the reason I want to do this one is because this is kind of typical of what happens in a power generator plant. These plants usually rotate with a frequency of 50 Hertz. So that means the direction changes 50 times in a second. So the electricity that comes out of this, the AC, it switches direction 50 times because at the power plant the wheel was spinning with 50 Hertz. If you slow this down to 25 Hertz, then you would get half the voltage. Is that right? Because your time, how would you get more voltage? Oh yeah, if you slow it down, you make this number smaller, which makes this one bigger, which makes this one bigger, which makes the total smaller. Yeah. So if you slow it down to 25, then you'll get 150 volts then. So 300 here. Okay, so the reason I had to do this and this was so you can calculate the change. It goes from 1.5 to 0. The reason I had to do this was so you could calculate the time, which goes here. So this is kind of like a section B question where they get you to do a couple of things and then you come up with a final answer or something at the end. Yes? So I think what we'll do is we'll have a look now at some more exam questions for this chapter, because last time we looked at it there wasn't as many as we could do, but I think now there's much more we can do. So let's just open up the exams here. Past exams, IFY, physics. Let's look at my most recent exam I have, unfortunately, is only 2015. So let's see what we get here. Okay. 1 is mechanics, 2 materials, 3 electricity, 4 electricity, 5, here we go. Does anyone remember the first one here? Lenz's law of electromagnetic induction.
Field current.
Could you give me a sentence with a verb, please?
No, if the field is in the right, the current is in the opposite.
Okay, now we're getting closer, yeah. Not that one. He has the key word is opposite here. No, opposite the key word. The induced current flows opposite to the change in field, magnetic field. Yes. You remember this one?
Yeah.
Yes. You almost said it right. Okay. So, anyways, the first one here. What rule is this? We have to work out the current. Is the current going ABCD or DCBA? So, which is this? Left hand, right hand? Which rule is this? Right hand. So let's look at A to B. From A to B, which direction is the force? And look at the way the wheel is turning. So from A to B, which direction is the force? Think about how you want to make the wheel turn. No.
It's up.
Yeah. The force is up here. That's the only way to make the wheel turn this way. So that means the F is up. The field, which way is the field going? Towards the door. So the current is going in. So the current is going from A to B. So it goes A, B, C, D. It's going this way around. So the answer here is A, B, C, D. I don't need to write that down. So the only calculation now is at the end here for 2 marks, which I'll let you try with your calculators. I want the total flux linkage. So remember that's with the N, and the N here is probably given. No, the N, there it is, 250. We're also given the angle, and we're also given the area. So there's not too much to calculate here if we just use the right formula. Oh, wait, no, I already have the calculator open. 25.
Yeah, usually my calculator has the ground mode. What is it?
How do you do that? Grad is a different way to measure angle. There's 3 measurements of angle: degrees, radians, and gradients. Degrees, there's 360 in a circle. Radians, there's 2 pi in a circle. And gradients, do you know this one?
No, 1K.
No. Nice try though. 400 gradients in a circle. It's used, I believe, more in surveying, when you're talking about construction. The gradient of a road or a hill goes from 0 to 100. So a gradient of 50 is a 45 degree angle. So it doesn't really have a use in physics or maths. I think it's more used in surveying. Okay, do you have an answer though? You think so? Yeah, let's have a look here. So the formula, what is it? It's MBA cos theta. The N is 250. The B is a quarter. The A is given. And it's cos 25. And let's crunch that out. 250 times 0.250 times 20 times 10 to the power of minus 4 times cos 25 and 0.11 or 113 milliwebers. Okay, and that's it. So it was a 2-mark question, so not too much to do. So 2 marks are saying Lenz's law, the induced current opposes the change in the magnetic field. 1 mark for saying A, B, C, D, and then 2 marks for that calculation. 6 we haven't done. 7 is back to, oh yeah, but actually, it's fields. Vectors, mechanics, materials, atom, waves. This is fields, but it's not the fields we've done so far. So not a lot of fields in that paper, which maybe that's a good thing. More mechanics and waves. Okay, so let's go to the next year then. DIFC, physics, past papers, IFI past papers, physics, 2014, version 4 we'll start with. Did I click enter? Yes, I did. Alright. Right, that's electricity. Let's start with A. Mechanics, waves, fields, but not what we've done yet. Mechanics, waves. Here we go. Here's another fields one. A plane of a rectangular coil having 100 turns of wire carries a current of 1.3 amps, and this is parallel to a magnetic field of strength 2.6 times 10 to the minus 3 Tesla. The torque on the coil is that. What is the cross-sectional area? Okay, so the question here is, which formula is this one? You think you know?
The torque one.
Yeah, which is what? Something to do with a bank.
IBM.
Yeah, IBAN. So using the IBAN formula, give me the area, please. That seems a reasonable answer here for the area, should be small. So, our formula here, torque equals IBAN. So that means the A is torque over IBN. The torque is given 4.3 times 10 to the minus 4. The I is given, it's 1.3. The B is given, it's 2.6 times 10 to the minus 3. And then finally the N is given as 100, which is 10 to the 2. So if I hit that in, we get the answer. 100, yeah. (4.3) times 10 to the minus 4, 1.3 times 2.6 to the times 10 to the minus 3 times 10 to the 2. Yeah, 100. Yeah. 1.27 milli.
How did you change it?
My calculator to this form?
Yes.
This version of the calculator does it, the Casio 570. 1.27 milli. Oh no, I shouldn't use milli because it's area. Okay. Okay. Next part now is what is the magnetic flux when the angle is 35? Huh? Yeah? Correct, yeah.
Yeah.
Mare knows it. Not how, what, or why. Which? You said it twice now.
No.
You said it twice now.
You want the magnetic flux, and you have the area and the B.
You want the magnetic flux linkage, the total magnetic flux, yeah.
The total magnetic.
Yes. Yeah, you can use the previous info, so you get NBA cos theta. You know the NBA cos theta, so it's 100 times 2.6 times 10 to minus 3 times 1.27 minus 3. What cost 35? 2.7? 10 to the minus 4. So that is 27 milliwebers. No, it's not. It's 0.27 milliwebers. I should put it maybe in micros if I divide by 10 to the minus 6. If you're wondering how I'm converting these, watch. If I want this to be in micros, I'll divide it by 10 to the minus 6. Yeah, 270 micro Webers. Okay. Did you write this one down? Yeah. Let's see if there's anything else in this exam. So that's fields, that's mechanics, with materials mixed in as well, Young's modulus. That's electricity. That looks like mechanics. That looks like simple harmonic motion actually, so that's mechanics. This one is electricity, that one's atoms, that one's materials, and that one's fields. Yeah, let's have a look at the C here. So magnetic flux density, if you remember the definition, it's magnetic flux per cross-sectional area, so it's Webers per meter squared, also called a Tesla. And I was telling you before, they like to ask you to draw field lines, so they want you to draw the field lines to a long, straight, current-carrying wire. So I'll draw what they want, but you can add in the field lines. So what they have here is a wire. We'll have the current going from the bottom to the top. And sometimes to help the picture, they put in the sort of the ground. So this here you can picture going maybe through some a little hole in a piece of paper or something. It just kind of helps to give a sense of the three dimensions of the space. So the current is moving up. We did the picture for this, and in fact this is one of the hand rules for which way the current is going. It's the right hand grip rule. So if you think back, try to remember that and draw the field lines in your book, and then I'll draw them now in a moment. So the hint I'll give you is you have to use your right hand for this one. Oh, Sharif, what did I just ask you to do? smile at your teacher not knowing what to do? No, that's not what I asked you to do. What I asked you to do is draw the field lines in this picture. The current is heading up. Yes. Show me your beautiful picture. The heck is that? Yeah, beautiful. So, this is using the right hand grip rule. The current is going up. The field is curving this way around. So, in my picture, the field is like this. Okay. Got that? So let's have a look at the next part. The next part is I give you a length of wire, or you have a length of wire, you have a current, you have an angle, and you have the force, and this time they want the flux. This one here is, you have a wire, and the length of the wire is 5 times 10 to the minus 2 meters. And there's a current going through the wire of 3 amps. And the angle is 30 degrees as well. And you have the force on it from the magnetic field. It's 3.56 times 10 to the minus 6 newtons. And you want to know what is the flux. Is the flux or flux density? Flux density. So there is a formula here. I wonder if you remember which one it is. This one here is F equals Bill. You know the F, you know the I, you know the L, and you want the B. Although this one's at an angle, so this has a sine theta in it as well. Which you know, because the question says the angle is 30. Now you see, once you know what you're doing, it's easy, but if you didn't know that you have to use this formula, then it's not easy. So we can get B equals F over IL sine theta, and all of this we know. So calculate, please. Calculate. .7 times 10 to the minus 4. So if I put that in micros, microtesla. Yeah. Yeah, yeah. Minus 4. Here, what's the F? 3.56. Okay. Minus 6, yeah? That's tiny. Yeah, tiny. Alright. Over I, which is 3, times L, which is 5 times 10 to the minus 2, times sine 30. Quite different. 4.74 10 to the minus 5. Right, so that just changes this to 47. Divide by 10 to the minus 6. Yeah, 47 microtesla. Yes, Ms. Sharif, what's wrong?
I'm leaving now.
No, you can't. You can't leave until I tell you to leave. You can leave now.